Hello, my name is Anna Bunger, and this is Lab 4 Oscillations for Physics 2211. The purpose of this lab is to analyze the motion and change of energy of an oscillating weight attached to a spring. The key concepts involved include Newton's second law, the momentum principle, force, springs, energy, and work. Here are some of the important equations used in the calculations for this lab. The spring force is equal to the negative spring constant, negative k, times the change in length times L hat. Spring energy is equal to the spring constant times S, which is equal to L minus L initial, and then squared. Kinetic energy is 1/2 mass times velocity squared. Gravitational potential energy is negative mass times height times 9.8, which is the gravitational constant. The energy principle is the total energy equals gravitational potential energy plus spring energy plus kinetic energy. The system was chosen to be the weight in the spring, and the surroundings was everything else. Some of the initial conditions, such as the gravitational constant, spring constant, and relaxed length of the spring, were given, while others, such as the vector for the spring and the system energies, had to be calculated. These calculations are seen here on lines 87 through 97 of the code. Here is a screenshot of the tracker data. On the left side, the magenta lines represent the x and y axes, and each red dot represents the mass at a given video frame. On the right, the graphs shown are the x values versus time and y value versus time graphs. Here is the while loop used to calculate values. The initial values, seen in lines 108 to 112, were defined in the setup slide. The rest of the calculations include net force calculations, lines 117 to 121, position and velocity update calculations, lines 125 and 127, and changes in energy, lines 137 through 145. Here are the graphs produced from running the GlowScript code. On the right side, the time versus x position and time versus y position graphs are shown. The blue lines represent the model calculated on GlowScript, and the red lines are representative of the experimental data calculated in the tracker software. The model and experimental positions differ due to human error when using the tracker software. On the left side, change in energy versus time is shown. The blue line shows kinetic energy, red gravitational potential energy, and green spring energy. It is important to note that delta E, the orange line, is equal to 0. Conclusion. Does your model satisfy the energy principle? The energy principle states that energy in a closed system is conserved over time. This model is representative of that, as the change in total energy equals 0 throughout the entire trial. Using the data you obtained in Tracker, make two separate estimates of the oscillation periods. First, by estimating the period of oscillation from the x position data, and second, by estimating the period of oscillation from the y position data. So, in my calculations, I got the x position data had an oscillation time of 1.709 seconds, and the y position data had one of 1.519 seconds. Since they are so different, an average of the two should have been used in calculations to make up for this.